Welcome back. So this is going to be a follow-up of the first two sessions. This is still going to be focused on Cepheid variables, but this time we're going to discuss in details what used to be the main systematic effect of Cepheid, which is the metallicity effect or metallicity dependance. So I wanted to start this session by showing this really nice image of the Milky Way from Gaia, and also the two Magellanic clouds, large Magellanic cloud and small. And I think it's especially relevant for this session because we're going to use, in particular, the system composed of Milky Way and LMC and SMC. Really, the question here on Cepheid systematics is, are we actually looking at the same objects between the first and the second rung of the distance ladder? Because as you've heard this morning, the point is really consistency. The point is not to introduce any unwanted differences or unwanted systematics when you measure Cepheids at different levels, at different distances. So the question is, are we observing exactly the same objects? And the answer is not exactly, because what really differs between Cepheids of the first rung and Cepheid of the second rung is their metal abundance, especially Cepheids in the Milky Way and NGC 4258 are particularly metal-rich, about the same abundance as Cepheids in type 1a supernovae hosts. But we are also using the large and small Magellanic clouds, and Cepheids in there are particularly metal-poor. And why does that make a difference? Because metal-rich Cepheids are slightly brighter than metal-poor ones. And the question is also by how much? And does that impact the Hubble Constant measurement? Does that impact distance measurement? Yes, it does. And that specific dependence, what we call the Cepheid Metallicity Dependence, is parameterized by the additional coefficient gamma. So instead of a simple period-luminosity relation, like I lied to you in the previous session, it's not just A log P plus B, it's actually a little bit more complex. So it's A log P plus B plus gamma Fe over H, or O over H. So Teresa is going to cover this Fe over H or O over H. So these are the metallicity measurements, or the abundance of elements different than helium and hydrogen. So basically, anything that's not helium or hydrogen is a metal in astronomy, and that's measured by spectroscopy. So in that first part of the session, we're going to discuss this gamma coefficient and how it's measured, what it means, how it impacts the rest of the distance ladder. So first of all, the sign of the gamma coefficient, gamma being positive means that metal-rich Cepheids are fainter, and gamma negative means that metal-rich Cepheids are brighter. In our case today, we know that it's more likely to be negative, and it has been measured and also predicted from the theory. So we're more in the case of metal-rich Cepheids being brighter. There are two different methods to measure gamma empirically. First, you can stay in just one galaxy and use the fact that in nearly every spiral galaxy, there's a metallicity gradient with higher metallicity in the center and more metal-poor objects in the outskirts. So you can just look at Cepheids, for example, in the Milky Way or M33, where there's a beautiful gradient, and you compare how the period-luminosity relation behaves in the center versus in the outskirts. And that's something that's done especially with Gaia now in the Milky Way, where you can both have high-precision parallaxes, hence distances, versus also direct metallicity measurements for each Cepheid individually. In other galaxies, it's also possible, but also you don't have Gaia reaching like M33 for distances, but you can assume the same distance to all Cepheids in like other galaxies. The other method, the second one, is taking different galaxies that have distinct metallicities, and in that case, I'm thinking of the Milky Way versus the Magellanic clouds, much more metal poor. And by calibrating or comparing the intercepts of these period-luminosity relations in different galaxies that have different metallicities, you can calibrate these dependence. These two different methods are illustrated here. On the y-axis, you have the period-luminosity intercept. So we assume the slope is universal, which is a pretty good assumption at this level. And versus on the x-axis, you have metallicity, Fe over h. So you have the Milky Way here with the PL relation obtained from 67 Cepheids obtained with HST. It's pretty metal poor with about solar abundance. And then LMC and SMC, again observed with the Hubble Space Telescope, with about 70 and 80 Cepheids respectively. And even from these three big points here, you can already see a trend that they follow this black line. And overplotted on top are the orange squares that represent Milky Way Cepheids. They're binned. Every square contains about 20 Cepheids, because there are like 300 Cepheids with good data. So we can plot the 300 here. But yeah, basically they follow the same trend. It's a little bit steeper. But overall, the two methods give a negative value for gamma with about minus 0.2 to minus 0.3. And something we can notice here is that I overplot the histogram of the supernovae host galaxies here. As you can see, they're very consistent with Milky Way metallicity, so very metal rich. That's why it's a little bit tricky to use LMC and SMC, because they differ. They are much more metal poor. So because we're including them in the Hubble constant measurement, we want to make sure that these two metal poor galaxies are not introducing any problems. And that's why we have to calibrate this slope. So yeah, the takeaway message here is just from this plot, the slope here is the gamma parameter. Now, gamma has been measured many different ways by different teams with different techniques. And it can be measured in different filters or systems. So Teresa has introduced the Wesenheit index, which is a combination between a magnitude and a color index. And here I'm presenting in green the near-infrared Wesenheit, and in blue the optical Wesenheit. And all these are values for the gamma parameter, obtained by many different teams, different papers. Everything here is published. And there's also a legend for the different methods, so combining different galaxies, using the gradient, using Gaia, using other kind of distances, and the theory, so predictions from the models that also agree really well with the observations. So I'm just showing this because there had been some discussions, and I wouldn't say tensions, but there had been some disagreements in the past regarding the value of gamma. And still now there are some differences and there is still some scatter, but overall it's pretty well understood now, and it's pretty consistent within all these different studies that gamma is between minus 0.2 and minus 0.3. Now, you might wonder why do we talk about this gamma parameter? We just want to know about H naught. So on the top axis now, I've added the value of H naught for the corresponding values of gamma. And you see that with a central value of 73, if you wanted to fix the Hubble tension, to solve the Hubble tension just from metallicity, the metallicity perspective, then you would have to really assume a crazy value of gamma to get even a little bit closer to Planck. So even here, I would say the crazier value is like minus 0.4, minus 0.5. And you don't even get below 72.6. So yeah, the message here is really that the impact of the gamma parameter of the metallicity dependence is minimal for H naught. It's below 0.8 kilometer per second per megaparsec. And that's mostly because a lot of the supernovae hosts are very similar to the anchor galaxies, except, of course, LMC and SMC. But having the Milky Way calibration with Gaia and NGC 4258, which are very metal-rich, it allows to balance the weight of the 4 anchor galaxies, and as a result, the sensitivity of H0 with respect to the exact value of gamma is now very limited. So why should we care? Because it doesn't really impact H0, so why should we care about the metallicity dependence? Well, first of all, to make all the anchor galaxies consistent. Like if we only use, like in the past, people have used only the LMC to calibrate H0, and the LMC is metal poor. So each anchor galaxies would give you a different H0 if you don't correct for metallicity. So we want to make the 4 anchor galaxies consistent. The other reason why we should care about gamma is because simply for distance measurement. Let's forget for a minute about cosmology and the Hubble constant, and let's say you just want to measure the distance to some local group galaxies. It turns out a lot of galaxies that are nearby are also very metal poor, like Sexton A and B, WLM, IC 1613, a lot of these galaxies that are super interesting for a lot of different reasons, and they are used in very different fields of astronomy. Well, if you need to measure the distance, depending on how you calibrate the PL relation and what value you assume for the metallicity dependence, you will get a different answer. So basically, just for measuring distances, you need to care about the metallicity. For example, let's say you want to study something that's completely unrelated to cosmology, but your target is M33. It has a metallicity of about minus 0.3 dex. And then you want to measure the distance to this galaxy using 2 different references. First, using the Milky Way, that has a metallicity of about 0.1. Or you want to anchor it to the Large Magellanic Cloud, which is more metal poor. Well, using these 2 different galaxies to calibrate the PL relation, you would get 2 different answers. From the Milky Way calibration, you get 880 kiloparsec, and using the LMC, you would get 850 kiloparsec. And that could make a significant difference depending on what you're trying to measure, what science you want to do. It does matter. It does impact the results. And I do believe that in many fields in astronomy, people do care about having high precision distances. I mean, we have been developing Cepheid indicators and other techniques for the purpose of the Hubble constant, but now the more I evolve in that field, the more I understand everyone should care about distances, and measuring these distances with high precision should also benefit a lot of other fields in astronomy. So yeah, that's just an example of how different your answer can be, depending on how you treat the metallicity. Now, it has been seen from observations that it's about minus 0.2 to minus 0.3. But what does the model say? So nonlinear convecting models have predicted, like about 20 years ago, that gamma would be positive. But in individual filters, and now also in the Weisand height indices, when you correct for color, this term would become negative in agreement with observations and measurements. Now, more recently, other models, the Geneva linear models that also include rotation on the surface of Cepheids, that are a little bit more precise, they now predict a negative value for the gamma parameter, again, meaning that metal-rich Cepheids are brighter than metal-poor ones. All right, so this is good. This means that models and observations agree. So we're on the way to really understanding definitely how metallicity affects Cepheids. So again, I'm showing this plot of different measurements. If you want to have a full list of references, both for model predictions and empirical measurements, you can look at 2 of my recent papers. I've worked on that for a couple of years, and I've had like at least three papers on that. So there are a couple of literature reviews and checks, and also tables and figures on that specifically. So yeah, most values agree between minus 0.2 and 0.3 using these various methods. So today I'm just going to review a couple of these studies and tell you how they did to measure gamma. This also shows you how much people have cared about gamma, because all of these papers are about the same thing, so it has to be something that should be important. So I'm going to review a couple of these papers. Some of them had more extreme values or surprising results, so we wanted to make sure we understand what's going on. So we went back to the data and tried to understand, some of them were not consistent with the mean, and we wanted to see why they were different. So I'll show you a couple of them. The first paper I wanted to discuss is by Vilgorsky, 2017. They used cepheids in the LMC and SMC, so both are metal poor. SMC is even more metal poor than LMC, and they just fixed the slope of the period-luminosity relation to the same value, and then they compared the intercept. So it's good enough in the sense that they cover a not wide but decent metallicity range. However, they find a metallicity dependence of 0, so we were surprised and we went back to the data. They also used mean metallicity, so fixed PL relation slope and then a unique metallicity value for each galaxy. Also, the one issue that we identified is that the depth of the Magellanic Cloud, the shape of the Magellanic Cloud, was actually affecting the measurement. So it's not that much of a problem for a large Magellanic Cloud, but the SMC, the small Magellanic Cloud, is particularly weird in terms of shape. So it's very elongated along the line of sight. It's like a cigar, a little bit tilted. So when you look at it, you actually look at cepheids that are really close to you, but also far away from you. And because it's nearby, this shape and this geometry of the SMC does affect the measurements. So there's a whole paragraph about that in the paper, but you don't have to read that. I'll just show you the figure. So this is basically how you see the small Magellanic Cloud. It looks like this, and the blue points are the cepheids, and the yellow stars are the eclipsing binaries that get us the geometric distance. And here I did a test. I considered 3 regions in the SMC, the core in green, and then a slightly more extended region in pink, and then almost a full sample in purple. And then I checked how this impacted the PL scatter and also the gamma value. So these are the values of gamma as a function of the radius of the region considered. So the full sample would be here, and it's consistent with 0, and that's basically what they did in that paper. And then restricting more and more to the central regions would slowly decrease or make gamma more negative here. And if you cut only the green part of the SMC, only the center, which would limit the depth or the effect of geometry, would get you closer to the values also found by other papers. And here there are 2 colors, one in blue and one in green. It's with versus without the geometry correction. So something additional we can do in addition to cutting only the core is applying additional geometry correction. So you assume a model or an inclination for the small Magellanic Cloud. And instead of assuming every cepheid is at the same distance to us, you assume each cepheid has its own distance. So you account for that elongation of the SMC shape. And so applying this geometry correction also keeps the gamma value lower and more negative, so in better agreement with what we know. So this partially explains why they had a 0 value for the gamma term. So my point here is really make sure you're not using every cepheid from the SMC, but just the core region. Otherwise, you'll have geometry depth effect that will bias everything. Now, another study I wanted to discuss is that Friedman et al. 2011. So they measured the metallicity dependence in different filters. And they got sometimes positive, sometimes negative values depending on the filter. And the way they derived gamma here was using only LMC Cepheids. And I think it's a little bit ambitious because LMC Cepheids almost have the same metallicity. So here the problem is the metallicity range is very, very narrow. So you don't have enough of a lever arm to really to measure gamma. And then they use the PL residuals to get that. So here's the distribution of the metallicities of LMC Cepheids from Romagnello 2022. And as you can see, there's a range of about 0.3 dex, which is a little bit too short to get a meaningful value for gamma. And also, I think the error bars, especially in the near infrared, are probably underestimated given the data. But it's okay, now we know, and we have learned from spectroscopy that LMC Cepheids almost have the same abundance. So as a single system, the LMC cannot be used alone for measuring gamma. Another one, more recent, by Wolfgang Gieren in 2018. Now we're combining 3 galaxies, Milky Way, LMC, and SMC. So we're now covering a decent metallicity range of about almost 1 dex. And even from that plot, you probably can see on the PDF, probably not here on the screen, but even here you can see that Milky Way Cepheids are brighter than SMC Cepheids, which is the trend that we keep seeing. The problem here in this paper is that the distances are based, they're not from Gaia, they're based on another technique that's called the Bade-Wesselink method. And it's a really interesting technique. It's based on comparing the, by spectroscopy, looking at the variation of the pulsation of the star, maybe I'll start with the other one. From interferometry here, we compare the variation, the angular variation of the size of the Cepheid. And here by spectroscopy, the linear variation of the size of the Cepheid. It's a little bit tricky, and it requires extremely good measurement. And of course, you can only do that in the Milky Way so far. The problem with this technique is that it relies on a projection factor. And the projection factor is not very well calibrated or even understood from the physics point of view. So even though they find a really consistent value for gamma, same as other studies, I just wanted to say we have to be careful with this paper because they used this technique that's really not well calibrated yet. Also, they use a small sample. It's still okay, but we want to use bigger samples to make sure we have more statistics. But yeah, the point is that the distances are highly unreliable. This is not a problem we should have in the future because, again, Gaia DR4, the 4th data release, will come up in December. So each Milky Way Cepheid should soon have a very precise and reliable distance. And now, very recently this year, RIPEPI 2026, together also with the joint paper by Erasmo Trentin, they used Milky Way Cepheids that cover, as I said, they have a gradient, so they cover a decent range of metallicities. And they fit the period-luminosity metallicity relation now with three parameters. And they find a quite negative value, minus 0.36. So we double-checked that just to make sure we were able to reproduce it. We find that actually few Cepheids have very high or very low metallicity. So very few Cepheids actually provide a good lever arm for that. And most importantly, the lower metallicity Cepheids are further away because we're here. This is the view of the Milky Way and the different arms. The sun would be here. And if you want to get very metal-rich or very metal-poor Cepheids, you have to go further away in different arms or closer to the center where there's more extinction or further away where the parallax signal-to-noise is lower. So to get those low metallicity Cepheids, then you introduce more uncertainty. That's something you can see here with the parallax signal to noise, or this is uncertainty over parallax, and over that line, SNR is below 5, but unfortunately this is also where the low metallicity Cepheids live. So the more you include them, the more uncertain parallax you are going to include in your sample. But there's no official guideline on which Cepheid parallax you should use or not, but it's just a risk you're willing to take. As long as you include your uncertainties properly, it's fine. Overall, this negative value is not very concerning because overall it agrees within the uncertainties with the other measurements. It's just a little bit steeper, but using Gaia DR4, we expect that this will be solved with much higher precision astrometry. And now, last paper, sorry for this, it might be a little bit too long for a review, but just to show you the diversity of methods that have been used. So this is two recent papers by Medor and Friedman. The method they use is different. Again, this is just they're comparing Cepheid distances with TRGB distances to a couple of galaxies. Here you have the difference between Cepheid versus TRGB distance as a function of metallicity, and there are a lot of nearby galaxies from the local group. The problem is, and they find a 0 metallicity effect. The problem is here you have to assume that the TRGB distances, again, do not depend on metallicity, and that's something we don't know for sure. Also, some of the data are inhomogeneous, and some galaxies have very small number of Cepheids, so like I would not necessarily use like some of these most metal-poor galaxies like Section A and B and WLM. They have just a couple of Cepheids, so it's not super precise. We also should be careful about how we treat Gaia parallaxes. Some people follow the official Gaia collaboration correction. Some people use other alternative treatments, but this really does impact the results. So I would say follow the Gaia correction closely. That's my advice. And again, they also do the same thing with the SMC by using the whole galaxy, the whole SMC, instead of just taking the core, which also pushes the gamma coefficient to 0. But now that's something we identified and that we understand quite well. That plot summarizes, again, so metallicity here, and you have the different anchor galaxies. In blue, this is what we have, and then in red, this is the 0 metallicity effect. If you use the SMC core only, you do that cut and the geometry correction, this brings back this side up here to the value that we had, and then if you apply the official Gaia calibration, same, it brings this side lower, and then you find again a negative value for gamma of minus 0.2. So this is now well understood. So these are my lessons and the takeaway message for measuring gamma. There are some limitations. It's hard to find a wide metallicity range. People have used narrow metallicity range in the past, but it's preferred, if you can, to use something larger than 0.5 dex. There have been imprecise distances, like the bad vesseling techniques and the previous Gaia data. And also there's been problems with the Magellanic Clouds geometry, but now we can solve this by using, for the first point, using Milky Way, LMC, and SMC combined to really have the widest range of abundances. Here I'm quoting Gaia DR3, but just wait a couple months and you'll have Gaia DR4, and that will solve all of your problems with distances in the Milky Way. And yeah, in the Magellanic Clouds, I mostly discussed SMC, but you can also apply geometry corrections in the large Magellanic Clouds to have a cleaner treatment of your Cepheid sample and really make that cut in the SMC to avoid taking the whole sample. So to perform the best calibration, also use the full light curves. Some samples only use random or single epoch magnitudes. Avoid just like for H0, avoid combining too many photometric systems. That happens if you want to use too many galaxies at the same time. Then you have a larger sample, but then you're combining too many different systems. And then metallicities, a lot of direct spectra or direct abundances are now published for Milky Way Cepheids and also LMC and SMC Cepheids. So use recent and consistent metallicities. Don't mix up Fe over H or O over H. These are my recommendations. This is just one paper that I published in 2021 comparing Milky Way, LMC, and SMC. Again, to me, this is the golden sample because they cover such a wide metallicity range. The two LMC and SMC lines, they're offsetted just so you see how the Milky Way compares, but Milky Way is reproduced again as a dashed line, and you can really see the difference, how it's shifted. And then what we do is we fit PL intercept versus Fe over H, and again, the slope is gamma, and it really aligns really, really well. I've also looked into the dependence of gamma with wavelength, and overall I find that there's a good consistency, good agreement between the different filters. Even single filters versus Wesen height indices. And just as a takeaway message, this is the error budget of the Hubble constant, and in yellow with a red border, this is the contribution of the metallicity term in the Hubble constant measurement. In 2019, it was here, so it was still one of the main contributions to the uncertainty on H0. Today, or as of the last SHOES release in 2022, it's here. So you can really see that it went down and it's now better controlled, mostly thanks to Gaia, adding also the small Magellanic cloud and having better constraint, better metallicity measurements. Overall, really reduced the uncertainties. How do we measure Cepheid metallicities across the distance ladder? For nearby Cepheids, we do direct spectroscopy of these stars. We can resolve them individually. However, in supernovae host galaxies, we don't see them individually. We cannot do spectroscopy just like that. So we have to rely on brighter objects. So we use H2 regions, which are much brighter. How do these two methods agree? So this is just a comparison in the Milky Way. So this is the Milky Way gradient showing in blue measurements from the Cepheids and in black the H2 regions. And you can see that, okay, there is some scatter, but it's also intrinsic to the gradient, but also it agrees really well. So this is a transition we make when we move to the second rung of the distance ladder. We do H2 regions for metallicities, but so far it's not been a problem, and it's been in good agreement. So my conclusion on that is that gamma used to be the main systematic for Cepheid measurements, Cepheid distances, because the LMC was the only anchor at that time. We didn't have Gaia. Now that we have the Milky Way and we have NGC 4258, it's much easier to control that systematic. It's been measured many different ways, and we understand it from also the model's point of view, and also the impact now is very limited for H0. And I would say there is a consensus on the sign and on the value of gamma.